In the vast universe, stars are not eternal. They are born, they live, and they die in a fascinating cosmic cycle. The life cycle of a star begins in massive clouds of gas and dust called nebulae, where gravity pulls material together to form a protostar. As pressure and heat increase, nuclear fusion ignites, and a new star is born. Most of a star's life is spent in a stable phase called the main sequence, where it shines by converting hydrogen into helium. But what happens next depends on its mass. Smaller stars, like our Sun, eventually swell into red giants and gently fade into white dwarfs. Massive stars, however, end in dramatic supernova explosions, sometimes leaving behind neutron stars or even black holes. Today we will talk about the life cycle of a star in 5 minutes. So before we start, make sure to hit the like button and subscribe to my channel. 1. Stellar birth in nebulae. The life cycle of a star begins in one of the most spectacular structures in the universe, a nebula. A nebula is a vast cloud of gas, mostly hydrogen and helium, and dust floating in space, often spanning light years across. These regions are extremely cold and diffuse, but they contain all the raw material needed to form stars. Over time, slight disturbances, such as shock waves from nearby, supernovae, or gravitational interactions cause parts of a nebula to collapse inward under their own gravity. As the gas contracts, it begins to heat up and form dense clumps known as protostellar cores. These regions are the earliest stage of star formation, where matter is continuously pulled inward, increasing pressure and temperature at the center. 2. Protostar formation and gravitational compression. As the collapsing material in the nebula continues to condense, the protostar phase begins. A protostar is essentially a baby star that is still gathering mass from its surroundings. Gravity is the dominant force driving this stage, pulling more gas and dust toward the core. As material accumulates, gravitational potential energy is converted into thermal energy, causing the core temperature to rise significantly, often reaching millions of degrees Kelvin. At this stage, the protostar is surrounded by a rotating disk of gas and dust called an accretion disk, which may eventually form planets, asteroids, or other celestial bodies. Jets of charged particles are often ejected from the poles of the protostar due to magnetic field interactions, clearing away excess material. However, nuclear fusion has not yet begun in the core, meaning the protostar is not yet a true star, but is steadily approaching that critical threshold. 3. Ignition of nuclear fusion and birth of a main sequence star. The defining moment in a star's life occurs when the core temperature becomes high enough, around 10 million Kelvin, for nuclear fusion to ignite. At this point, hydrogen atoms begin fusing into helium in a process that releases enormous amounts of energy. This outward pressure created by fusion balances the inward pull of gravity, establishing a state known as hydrostatic equilibrium. When this balance is achieved, the star officially enters the main sequence phase. This is the longest and most stable period in a star's life cycle. The star now shines steadily, producing light, heat, and radiation across the electromagnetic spectrum. The size, temperature, and brightness of a main sequence star depend on its mass. Smaller stars burn fuel slowly and can live for tens to hundreds of billions of years, while massive stars burn extremely bright, but may only last a few million years. 4. The long main sequence phase and stellar stability. During the main sequence stage, stars spend approximately 90% of their entire lifespan in a stable state. In this phase, nuclear fusion in the core continues to convert hydrogen into helium, generating energy that radiates outward as light and heat. The star's outward pressure from fusion perfectly balances gravitational collapse, creating long-term stability. Our Sun is currently in this phase and has been for about 4.6 billion years. It is expected to remain in the main sequence for another 5 billion years. The behavior of stars in this stage depends heavily on their mass. Low-mass stars, known as red dwarfs, are cool and dim, but incredibly long-lived. High-mass stars, however, consume their hydrogen fuel rapidly, leading to shorter but more intense lifespans. The main sequence can be seen as the adulthood of a star, where it maintains balance and produces energy consistently. 5. Expansion into a red giant or supergiant. Once a star exhausts the hydrogen in its core, the balance between gravity and fusion begins to shift. The core contracts while the outer layers expand dramatically, causing the star to swell into a red giant for low to medium mass stars or a red supergiant for massive stars. During this phase, helium begins to fuse into heavier elements like carbon and oxygen in the core, while hydrogen fusion continues in surrounding shells. The expansion causes the star's surface to cool, giving it a reddish appearance despite its increased size and luminosity. Red giants can become hundreds of times larger than their original size, potentially engulfing nearby planets. This stage marks the beginning of the star's final evolutionary changes as it starts burning heavier elements and gradually destabilizes. 6. Fusion of heavier elements and core instability in massive stars. In massive stars, the core continues to undergo successive stages of fusion beyond helium. Carbon, neon, oxygen, and silicon can all fuse in increasingly short-lived stages, producing heavier and heavier elements up to iron. However, iron fusion does not release energy, it consumes it. This creates a critical problem. Once iron accumulates in the core, the star can no longer sustain outward pressure through fusion. As a result, the core becomes unstable and rapidly collapses under gravity. This collapse happens in a fraction of a second and triggers one of the most energetic events in the universe. Meanwhile, the outer layers of the star are still falling inward, setting the stage for a catastrophic explosion. 7. Supernova explosion and stellar death. When the core collapses, it rebounds with tremendous force, producing a supernova explosion. This is one of the most powerful events in the cosmos, briefly outshining entire galaxies. The explosion blasts the outer layers of the star into space at extremely high speeds, scattering heavy elements such as gold, uranium, and iron across the universe. These elements later become part of new stars, planets, and even life itself. Depending on the mass of the original star, the core left behind may form a neutron star or a black hole. A neutron star is an incredibly dense object composed almost entirely of neutrons, while a black hole is a region of space where gravity is so strong that not even light can escape. This marks the dramatic end of a massive star's life cycle. 8. Final stages: white dwarfs, neutron stars, and black holes. For smaller stars like the Sun, the end is much quieter. After expanding into a red giant, the outer layers are gently expelled into space, forming a planetary nebula. The remaining core becomes a white dwarf, a dense, Earth-sized remnant that slowly cools over billions of years. It no longer undergoes fusion, but still emits residual heat. In contrast, massive stars end as either neutron stars or black holes, depending on their final mass. Neutron stars are incredibly dense, with a teaspoon of material weighing billions of tons. Black holes represent the ultimate collapse, where gravity is so intense that it warps space and time itself. Over cosmic timescales, these remnants continue to evolve, shaping galaxies and influencing the formation of new stars, continuing the endless cycle of stellar birth, life, and death across the universe. But if you like this video and would like to see more like it, please give it a thumbs up, leave a comment, and click the button to subscribe.